In this video, we review how to do arithmetic with complex numbers. All the arithmetic relies on a definition of the imaginary unit, I. That is, I squared equals -1. Addition and subtraction are very simple in the real imaginary representation. Two numbers, a plus bi plus c plus di, can be added just by adding their real parts, a plus c, to give the real part of the result, plus adding their imaginary parts, b plus t, to give their imaginary part of the result. Multiplication. Multiplication is simple in both representations. In the real imaginary representation, just multiply out, taking I squared equals -1 into account. For example, a plus bi times c plus di gives, after multiplying out and collecting the real and imaginary terms separately, ac minus bd for the real part, plus ad plus bc for the imaginary part. In the exponential form, it's even easier. The amplitudes multiply and the phases add. For example, a times e to the I phi times v times e to the I chi. Just multiply the amplitudes to get the result amplitude and add the phases. Division in the real imaginary representation is a touch tedious. For example, if you want to calculate a plus bi divided by c plus di, it's not straightforward. The trick is to multiply a numerator and denominator by c minus di, which then gives, after multiplying out, ac plus bd plus bc minus ad times I, all this divided by c squared plus d squared. Division is much simpler in exponential notation. For example, a times e to the I phi divided by b times e to the I chi. Just divide the amplitudes, a over b, and subtract the phases. An important concept is the complex conjugate. The complex conjugate of a complex number c is denoted with a superscript asterisk, c star. For example, if c equals a plus bi, then c star equals a minus bi. To form the complex conjugate, just invert the sign of the imaginary component. In exponential notation, if c equals a times e to the I phi, then the complex conjugate equals to a times e to the negative I phi. In essence, you just need to change the sign of the phase. Remember that a is a real and positive number. Dealing with the complex conjugate is simple. For example, the product of two complex terms c and d, complex conjugate, equals the product of the individual complex conjugates. Also, the sum of two complex terms, complex conjugate, equals the sum of the individual terms, complex conjugated themselves. One of the most useful relationships in quantum mechanics is between a complex exponential and a trigonometric function sine and cosine. It goes like this: e to the I phi equals the cosine of phi plus I times the sine of phi. Pictorially, in the coordinate system that represents a complex number, e to the I phi is a vector of unit length with the phase angle phi. Cosine phi is the projection of this vector onto the horizontal axis, and sine phi is the projection of the vector onto the vertical axis. As a special case, look at what happens if phi equals pi, that is 180 degrees. Then the expression above reduces to e to the I pi equals -1, a relation that shows a surprising connection between e, pi, and the imaginary unit. With this relation above, it's easy now to reformulate cosine and sine functions as complex exponentials. We get, for the cosine of x, we get 1/2 times e to the plus ix plus e to the negative ix. Similarly, the sine of x equals 1 over 2i, don't forget the I here, times e to the plus ix minus e to the negative ix. These relations are the reason why complex numbers are so useful for describing periodic phenomena, not only in quantum physics but also in classical physics.